All right, here's implicit differentiation, which is basically what we've done all along. But we're going to do is specify some special things here, and I'm going to try and make this clear because I have some pretty gross handwriting going on here. See if I can help you out. The first step is to take the derivative with respect to x or any other variable, can actually be, but we'll do with x for right now. And to solve for dy dx in this case, but it could be actually any other variable. It's your input variable, whatever you think of it as your input variable. So right now we're going to talk a lot about it with respect to x, and we can expand from there. Okay, so next in line, here's an example. So I got this function y cubed 4x cubed plus 6x. Here's how the derivative unfolds. I just went ahead and put it out there. When I do implicit differentiation, the only difference is, see that y cubed? Well, this is what you might expect, 3y squared. This is the derivative of y cubed, right? Same thing you'd expect. The only thing is, if I'm going to take the derivative with respect to x, that means any variable that is not x, I have to include this d of that variable, in this case y, over dx. Okay? Anything that's an x, just take the derivative like it's always been. So look at this, 12x squared, well that's the derivative of 4x cubed. 3 times 4 is 12, x to the second, because I lowered the power by 1. Derivative of 6x is just 6. Okay, so this is a finished derivative. Now, just keep an eye out that dy dx is because I took the derivative of something that wasn't an x, so I had to put it right after the derivative. That's going to be the theme. Always put the d of the letter that is an x after it over dx. The last thing we do, solve for dy dx. So I had to divide both sides by 3y squared. And here it is, dividing both sides by 3y squared. Finish this off. That means dy dx is 12x squared plus 6 over 3y squared. Weird, it's going to have x's and y's in it, but that's okay. Because later on when I say, hey, what's the derivative is still to get the slope of the tangent line. But now when I give you a coordinate point with an x and a y in it, we're going to use both. Plug them both in, one for x and one for y. Not respectively, I did that in backward order. And you'll actually get the slope, but you have to have the x, y coordinates both to get that slope of the tangent. All right, so let's look at another one. Let's throw some weird letters in there. W, Z, Y, and X. I'm going to take the derivative with respect to X. So watch what happens when I hit letters that are not X. Derivative with respect to X. This is how we mark it. D dx of both sides. You always do the same to both sides. Oops, sorry. And derivative of 3W is 3 with dw dx, because it's a letter other than X. How about negative 4z squared? Well, it's negative 8z, like we know, but don't forget dz dx, because it's not an x. How about the derivative of 2y? Well, derivative of 2y is 2 dy dx, because it's not an x. But then when we get to x squared, 4x cubed back there, derivative of that is 12x squared. Okay, so our things are unfolding kind of nicely. The idea is then I'll say find dy dx or find dz dx. Basically, I'll ask you to solve for one of those things called a differential. Now, I just did a whole bunch of work in there, so let me slow back. I can always go back and explain some more. But these are called differentials. The one I ask you to solve for or find is the one that algebraically you're going to solve for. So if I back this up just a tad bit here, that means minus 12x squared from both sides because I want to get dy dx by itself. That's what I mean for solving for that one. So there it is, divide both sides by 2. And what we should get, because that's how I get the 2 away from dy dx. So what I get is this whole left-hand side in the box. Take away the minus 12x squared, got the minus 12x squared, and then I divided both sides by 2. So I got this divided by 2, and that is going to be my dy dx term. Pretty cool, huh? It's a mess to look at, but implicit differentiation is do derivatives if it's a letter other than what it's with respect to. Then you have to put the differential d letter dx afterward, or d letter. Yeah, we're going to go from there. Give me another example. Xy squared plus 8xy equals 12. This allows, we can do derivatives with all kinds of letters in them. The rules still apply. Even two things that are multiplied, we have to do a product rule for each little product. So let me get you a couple spots out here. Let me unfold this one a little bit. I just did the derivative of xy squared. Crazy, huh? You do the derivative of the first. I'm going to highlight little pieces and then get rid of them. Okay, so derivative of x is there, times the second unchanged, got it, plus the derivative of the second, remember right there is 2, y, because it's not an x, There's the differential dy dx afterward. So a derivative with respect to x. That's all that I'm doing throughout these examples. So that's just the derivative of 2y, or y squared, 2y dy dx. Then here we have the derivative, the second unchanged. So should I go back and look at that again? So the derivative of xy squared alone is 1y squared plus 2y dx, because I'm doing the derivative of the first times the second unchanged plus the derivative of the second times the first unchanged. Now let's go to the other one. Let's keep rolling. 8xy. That derivative you see here is 8y plus dy dx 8x. Let me highlight that, because I'm doing the derivative of the first 8x is just 8. The derivative with times the second unchanged, plus the derivative of the second, which is y. So what I'm thinking of as first and second, this might be a little confusing to look at, is I'm thinking of first, second, first, second when I did those derivatives. Okay, so I'm going to pull that back up. What I got is those two terms. Those are huge. Oh, my word. The next piece is, now, let me back up just a tad bit there. So when I did derivative of 8xy, it was 8x, derivative is 8 times y, the second unchanged. And then I did the derivative of y, which ended up just being, let me back that up just a tad bit. The derivative of y is just 1 dy dx, because it's not an x, I have to put the dy dx in there. So what I didn't put in there was a 1. Maybe I should put that in there for you. 1. Then the derivative times the first unchanged, because I don't want to. Yep, so we'll keep on rolling. So there it is, the first unchanged. Got that one right there, 8x. Whew, crazy, huh? So derivative of the first times the second unchanged, those 2 marks there, times the derivative of the second times the first unchanged. And then I'll go ahead and finish this off and simplify it out a little bit. Things that you want to keep track of, I can actually subtract away a few things. Do you notice that the dy dx term in here, that's hard to find now because I got all these markings in there. What I'm going to do is get dy dx by itself, and the first thing I do is I'm going to go in with some nice bold purple. I'm going to subtract away the y squared and subtract away the 8y. You're going to see them here, minus y squared minus 8y. And that leaves me, but you see on the 2yx dy dx comes from here, and the 8x dy dx comes from here. All right, and then I'm going to get dy dx, pull that out, factor it out. See those dy dx's? Remember factoring that common term out. Okay, that leaves me 2yx plus 8x inside. Right-hand side is still negative 8y minus y squared. The last thing I do is divide both sides by 2yx plus 8x. To get this lovely expression. That's my dy dx. All I need is to somebody give me an x and a y coordinate point, and I can tell you the slope of the tangent line. Perfect, ready to go. Sorry, that was a little bit of a mess, but that one I was just a little more in depth. Let me go back to I'm going to give you a couple more. I actually kind of did this out of order, so I had to back up. So implicit differentiation is to take the derivative with respect to some variable other than, a couple of the variables. So here's y plus 4 equals 2x minus 1. Here's before implicit differentiation. You would do this. This is old school. Remember, you'd solve for y, and then I'd say, all right, take the derivative of both sides, and or just find the derivative. Y equals 2x minus 3. Simplify this to get it to be y equals, take the derivative, I'd say dy dx equals, what, 2? Okay, done. That's what we used to do. Well, we still get the same result with implicit differentiation, so let's look at it. If I take the derivative of this without simplifying or solving for y, remember when you encounter, this is with respect to x. The first thing I'll do, take the derivative of both sides with respect to x. When I get to y, it's just dy dx. What I'm leaving out is a 1 dy dx. Okay, and then the derivative of 4 is still 0. So I got a derivative of 4 right there. It's 0. See that? Got that. And then the derivative of 2x plus 1, the derivative of 2, remember it exists 2x has an x in it, the derivative that's just plain old 2. If I simplify or get dy dx by itself, to solve for that, I get dy dx equals 2. It's the same thing I had before, but derivative with respect to x means any letter I encounter that isn't x, I have to put the d letter dx afterward. Everything else, the rules don't change. So let's take the derivative here. Okay, when I hit 2x squared, I'm going to get 4x. That's the derivative of 2x squared. When I hit the derivative of 8x, I'm going to hit, it's just 8. The only thing that's different is when I do the derivative of that minus y term, well, it's going to be negative 1 dy dx, or negative dy dx, and there it is. 2x squared, derivative is 4x, 8x, derivative is 8, all is well. Now I will solve for dy dx. Okay, I got that, and there's the negative that sticks with that dy dx, and then I pass the, I divide both sides by negative 1 to get the negative to the other side. I want positive dy dx, and that makes negative 8 minus plus 4x. And if I do it old school, you want to see the old school way we used to do this? I would just add y to both sides maybe to get, and then I'd subtract 8x from both sides to get y by itself. Okay, does that look familiar? And then I'd say, hey, go take the derivative, and you'd go, all right, well, y prime is, what, derivative of 2x squared minus 8x, that'd be 4x minus 8. Hey, that's the same thing I got before, except I had it written as negative 8 plus 4x. So implicit differentiation is a way of taking derivatives without simplifying, and you can deal with other letters. But you're welcome to simplify in a lot of cases. So don't forget steps. Take the derivative with respect to x, and then solve for dy dx. Hey, we're going to do more of this on Wednesday. I'm going to leave you some problems in the homework that maybe you don't know how to do, but do your best. Come with questions. We'll rock and roll. Thanks so much.